So as always, I'll be recording our meeting so that if you ever want to go back and watch the recording of the notes that we're going over or the different examples I give for stuff, you will be free to do so at any point. There we go. All right. And as always, those recordings get posted right here in the class recording section of the website. So we are here at the very end of week 2. On Tuesday, we talked about distance and speed and acceleration and how things move and how we measure the different ways that things move. Today, we're going to talk about forces, which are what make things move or stop moving in the first place. So if you want something to change its acceleration and speed up or slow down, if you want something to change its speed, if you want something to change its direction and its velocity, you have to exert some sort of force in order for that to happen. And so today, we're going to talk about the different types of forces that are out there and how we can use a simple little picture called a free body diagram to show how forces interact on one object. All right, let me get my little big laser pointer out here. All right, here we go. So, forces. A force is defined simply as a push or a pull on an object that changes the motion of the object. Remember that first week of class, we talked about the Newton's laws of motion, and we mentioned that the first law says that an object will stay still or it'll stay moving until something comes along and acts upon it. And that something is called a force. So like I was just saying, if we want something to speed up or slow down or change direction, then we have to exert some sort of force on that object, some sort of a push or a pull in a certain direction that'll change the motion of the object. So there are different ways that we can kind of categorize the different types of forces that are out there. There are what's called contact forces, which are the most common ones that you're probably familiar with. And this is when two things physically contact each other in order for some sort of force to happen. So if you push open a door to open it, or you pull on a rope to pull something closer to you, that is contact forces. There's contact between your hand and the door and the hinges that the door is swinging on. There's contact from your palm to the rope to the object that the rope's attached to that you're pulling on. So we're going to talk a lot about the different types of contact forces that are out there. There are also field forces. So these are forces that affect an area around them. So the two most common ones are gravity and magnetism. So gravity, right, if I lift my pen up off the table here, even though it's not directly touching the earth, when I let it go, it gets pulled down to the ground. And that's because the gravity of the earth is acting on this pen and pulling it down. Even though nothing is physically touching it, that force is still exerted because of the field of gravity around the earth. Same thing with like magnets. If you've ever held two magnets in your hand kind of close to each other, if they're a certain way, you can feel them start to pull towards each other. And if you flip one of them around, then you can feel them kind of push away against each other when you get them in close. So that has, because magnets have what's called a magnetic field around them, so that when they start to get close to each other, they start to become attracted or repelled from each other, even though they're not physically touching. So contact forces are things that are physically touching and exerting pushes and pulls on each other. Field forces are when it's happening at a distance. We're not really going to talk a lot about field forces. Me describing gravity and magnets is pretty much the most we're going to get. But we're going to talk a lot about all the different contact forces that are out there. So the first type of contact force, and one of the more unusual ones, is called the normal force. It has kind of a weird name, but a very basic idea. The normal force is the force that prevents an object from just going straight through another object. So like when I have my pen here and I put it on my hand, the normal force says that is exerted from my hand on this pen, right? The pen is trying to go down because of gravity, but when it hits my hand, it stays there. And so gravity is pulling down on the pen, but my hand, even though I'm not like physically trying to lift it up into the air, even if I keep my hand still, my hand is pushing back up on the pen in order to keep it from going right through onto the ground. And so the force of something that's just sitting on top of an object is called the normal force. So that is what keeps my pen in my hand. If you put your water or your coffee or your cell phone down on a table, it sits there and doesn't fall to the floor because of the normal force. So whenever something is on the surface of something else, the normal force is pushing back up against gravity. The normal force is perpendicular to the surface, meaning it is in the exact opposite direction of the surface. For the most part, on a flat, even surface, that means that if you have this bucket that's sitting here, the normal force is going straight up into the air. If you set something down on a slope or like a plane, the normal force isn't going straight up into the air. Instead, it's going directly at a right angle to that slope. So it's always in the direct opposite direction of where the slope is going. So it has that normal force because in math and like in geometry and stuff, normal direction or a normal line is one that is at exactly perpendicular. So it makes a 90-degree angle with that force. If you have an even table, that angle means you're just going, the force is just straight up. If you're on a slope, that force is in the exact opposite direction of the slope. So the normal force is just the force of an object pushing back up on another object. It's not like trying to lift it up into the air. It's just stopping it from going down to the ground. So anytime something is sitting on top of another something, there's going to be a normal force involved. Oh, here's some more good examples. So like if you're pushing something up against a wall and you're like holding it in place on a wall, then the normal force is the wall pushing back on that object. So instead of going straight up, since the force of the object is going this way, the normal force goes in the opposite direction. Same thing with this little box here. Don't worry about all these other confusing symbols. We're not really going to talk about those. But since it's on this slope, this incline right here, the normal force is in the exact opposite direction of the slope. It's going up this way. It's not going straight up in the air. So the normal force is just the opposite force from the surface of some object when it's pushing against another one. Another really, really important force that is out there is friction, the friction force. So whenever two surfaces are sliding across one another, I push my computer across the table, you drive your car over the road, you ride your bike across the sidewalk, there is going to be friction that is occurring. So friction is opposing the motion of one surface on another. If you're trying to go to the right with your little block down here, friction is going to slow down that block in the opposite direction. It's going to try to move it towards the left. So it slows down or stops objects that are moving across it. It's moving in the opposite direction of where the object is traveling. There are some things that can affect friction. So the texture or the roughness of the surface can affect it. It's a lot easier to push your bike across a paved sidewalk versus like a dirt road or a gravel road, because that sidewalk is a lot smoother. And it also depends on the force pushing the surfaces together. One of the reasons why it's hard to move a really heavy object is because there's a lot of friction between that object and the surface that it's sitting on. And you have to overcome that friction in order to push the object. So essentially, friction happens because down at the microscopic level, not everything is perfectly 100% smooth. There's tiny little bumps and crags and nooks and crannies. And so as the surfaces move across each other, those kind of catch against each other and give us the force of friction. So as a surface moves across another one, you're going to have some friction going on. So a little bit more about friction. Again, friction resists motion. Friction helps to make it difficult to get things to start moving. And once things are moving, you have to keep putting in force in order to oppose that friction. So it causes moving objects to slow down. Again, this is why if you're pedaling your bike and then you stop pedaling, eventually you'll roll to a stop. Or if you're on your car and then like the engine shuts off or you shift down into neutral, yeah, you might travel along the road for a while, but eventually you're going to slow down and slow down and slow down and stop. And part of that is because of the friction between your tires and the road. Friction also produces heat. Simple way to show this, if you put your hands together and rub, there's a lot of friction because you have these surfaces rubbing against each other really fast. And as you do this, you can feel your hands warming up. And that's because of all the friction between your two hands when you rub them together. So there are a couple types of friction. There is what's called static friction, which is when you have two things that are stationary, not moving, that are in contact. So in order to get something to start moving in the first place, you have to overcome this static friction. Think about it as it's easier when something is moving to kind of speed it up and get it to go faster than it is to get it to start moving in the first place. And that's because of static friction. There is sliding friction when we've been talking about objects slide over one another and create friction that slows them down. There's also rolling friction. So when you think about a car wheel or a bike tire, you don't really think of them as like sliding or skidding across the ground unless you really slam on the brakes really hard. But there is still friction between the wheel as it rolls over the surface and the surface itself. So even though it's rolling and not technically sliding like we would think of it, there is still friction there. So it's hard to get things moving because of static frictions. Once things are moving, they'll constantly slow down because of either sliding friction or rolling friction. So a lot of things in human life depend on getting things from one area to another, pushing heavy things across long distances. And so humans have put a lot of effort into trying to figure out how can we reduce friction. Because of friction, our cars aren't as efficient. It takes a lot of energy in order to move heavy objects. And so the more you can reduce friction, the easier it is to move things around. So easiest step is using wheels. So rolling friction reduces movement a lot less compared to sliding friction. So if you've ever tried to like push, if you're moving or something and you're pushing a box across the floor, it's usually easier to move it if you pick it up and put it on a little rolling cart and then roll that cart along the floor instead. Because the box has a big flat bottom that's causing a lot of friction. The wheels just have that tiny little area where they're touching the ground, so it has smaller friction. Lubricants are a major way to reduce friction, especially in like moving machinery parts. So this helps to make an even smoother layer between the surfaces. Like I mentioned earlier, friction happens because of all those tiny little microscopic bumps that rub against each other. And so having lubricants in there helps to get those things to move easier by reducing all those bumps and reducing the amount of friction that is going on. This is why you need oil in your car. The oil helps to lubricate a lot of those moving parts in order to make them run a lot more efficiently and not like grind against each other. You can also, instead of putting a lubricant on something, you can also physically make it smoother by sanding it. So if you take some sandpaper and rub it against a rough surface, it's going to cut off a lot of those tiny little bumps and help make the surface really smooth, really frictionless. So the lower amount of bumps and the higher the smoothness you can get, the less friction that you're going to have. All right, so the two contact forces that I've talked about so far are the normal force, when an object is just preventing another object from going straight through it. So when something is resting on top of the other thing, the normal force is what is stopping it from going down. And we've talked about friction, which is a force that happens when things rub or slide across each other and opposes motion, causes motion to slow down, makes it hard for motion to keep going. So does anybody have any questions about the normal force or about friction so far?
No, sir. But I'm trying to keep up with my notes while writing.
Mm-hmm.
I'm trying to put it in like a perspective that I understand it.
Oh, that's perfect. That's an awesome way to do it. All right. No worries, Nancy. Thanks for being here. Good to see you. All right. So obviously there are a lot more normal or contact forces that we are going to talk about, but the normal force and friction are kind of two of the big ones for sure. So another type of contact force is, in physics, it's known as drag, but it also is called air resistance. So when an object moves through air or water or any other type of fluid, and in physics, air is thought of as having fluid-like properties, the fluid exerts a force kind of similar to friction on the moving object. So this fluid opposes the motion of that object. And we call that force drag. And so you can feel this if you're ever driving in your car and you stick your hand out the window and you can feel that air pushing back on your hand. Or if you're in like a swimming pool or something and you try to like run really fast through the pool, even though obviously you normally would swim in the water. But if it's a shallow area and you're trying to run through the water, it's hard, right? It's really hard to run in water. And that's because all that water is trying to oppose you moving through it. So the opposition force is called drag. So it's sort of similar to friction in that it opposes movement, it slows down movement. There are a couple ways that it is not like friction, however. Drag depends on the speed of the object. So the faster you're going, the more drag, the more resistance you encounter. This is not like friction. Friction does not matter the speed that you're moving. The friction force is going to be the same. Drag also depends on the size of the object, the shape of the object, the kind of fluid that you're going through, the density of that fluid. Again, unlike friction, which is just has to do with what surface is touching what surface, that will tell you the friction. Drag has all these extra little types of measurements thrown in there. So again, if you're moving through water, it's a little bit easier to move through than if you had to run through like mud or sand or something like really, really thick. That's going to cause a lot more drag. The shape also has a huge impact on the drag of an object. So that's why car manufacturers and especially plane manufacturers spend a lot of time looking at little models of their cars and planes and seeing how air interacts with them when they go through. That's why, for the most part, depending on what kind of car they are, all cars kind of have the same general shape, right? Like if you think of like a typical four-door sedan, like a Honda Civic or a Toyota Corolla, it's the same basic shape, right? It has kind of the rounded front, and then there's a little flat bit, and then there's the windshield, and then it kind of curves over the top, and then the back window kind of curves back down and then drops off at the bottom. So while trying to make it so that people can fit in there comfortably and the engine can still fit, they're trying to make it as streamlined as possible. So the more streamlined the body, the less drag that you have, the easier that it is for air to kind of travel around these objects, the less drag that you have, and the easier it is to have the car move at high speeds. The reason why you don't see very many like big boxy cars with lots of hard edges and stuff like that is because that increases the drag. The more like blunt, the more surface area you have interacting with the airflow, you're going to have a lot more drag. It's going to be a lot harder to push that vehicle through the air. So like I said, drag especially is something that physicists looked at when it comes to air. So when people are manufacturing cars, the whole reason that planes exist is because of drag. So the drag between the wing and the air creates this lift that helps the plane get off the ground. And that also means that skydivers, right, they jump out of the plane and then they free fall for a little bit and then they pull their parachute. At some point, while skydivers are free falling, the force of gravity pulling them down to the ground becomes balanced out by all of the drag that they're experiencing falling through the air. So as they go through the air and they're going faster and faster, the air is putting up more and more resistance to them going through it. That's why if you ever see a video of somebody skydiving and it has the actual audio of the jump, all you're going to hear as soon as they jump is just that's because of all the air that they're going through really, really quickly. So at some point, the person's not going to fall any faster. They're going to be going as fast as they can. So in physics, we call that terminal velocity. So terminal velocity is just a term meaning that the force of gravity, so that's what the FG stands here, force of gravity, is equal to the drag from the air. So you don't speed up anymore. You hit a certain miles per hour after you jump out of a plane, and you don't go any faster. And it's all because of this drag or this air resistance on that skydiver. So as things move through air and as things fall through the air, the drag from the air is what causes them to only accelerate up to a certain point. So without drag, if there's no air resistance, there's no drag, a raindrop would fall from the sky at about 340 miles an hour. So if it just continuously accelerated from the cloud it was in down to the ground, then it would hit the ground at a speed of about 340 miles an hour. However, since raindrops are so small and light, it does not take much air resistance in order to get them to reach their terminal velocity. So because of the air resistance and the drag that they experience going through the air, they actually only fall at about 17 miles per hour. So the drag and air resistance is just the resistance of air or any other type of fluid, really, to things moving through it. The faster that you get, the more drag there is. So that's one of the reasons why once you get cars going a certain speed, it's so hard in order to get them to go faster. Even the fastest land cars that they have out there, not like the super rocket powered ones, but if you've ever seen the Bugatti Veyrons, most expensive cars in the world, they're also some of the fastest cars in the world. And they have this super low to the ground, super bubble type shape. And that's because the faster and faster that they go, the harder the engine has to work in order to get them pushing through the air. They can get up to a little over 200 miles an hour. But at that point, the engine is putting in so much work to push the car through the air. I believe a full tank of gas at 200 something miles an hour in one of those cars would last about 8 or 9 minutes at full speed. And so this drag is something that anything moving fast, from cars to planes to rocket ships, has to deal with if they're traveling through the air. All right, other contact forces include tension. So tension is a really simple one. It's just the force from a rope or a string or some sort of attached object. So if you're holding something above the ground and it's attached to a rope or a string, there's tension between that object that's hanging there and the rope and the string that it's on. And that tension is the force that's holding that object up. So in this picture, we have this heart being held in place by these two tension forces right here. And then this guy is being held up by the tension force on this rope here. So with these guys, they still have gravity trying to pull them down to the ground. And they're not sitting on anything. So they don't have a normal force that is working against them and that is holding them up. But instead, they have these tension forces. And these are what are keeping them off the ground. Finally, the last type of contact force that we're going to talk about is the spring force. So obviously a spring, everybody knows what a spring is. You probably have them in some of the pens that you might use to write for your classes, right? I don't think you can really see it on this one, but down in here is a little spring that provides that resistance when I push against the top of the pen. And so spring force is some sort of force due to the elasticity of a material, meaning sort of like the bendiness or the compressedness of a material. So the amount of force depends on how elastic that spring is. The tiny little baby springs in here can't really do a whole lot of force, but the springs that go into like the suspension on cars or like big lifted trucks, those can deal with a lot of force. Those are incredibly durable and elastic springs. So one of the cool things about spring forces is that the direction of the force is opposite of its displacement. And what I mean by that is that if you have this little box right here that has this spring on top of it, if you push the spring down, the spring is going to push back up on you. And the harder that you push it down, the harder that it's going to push back, right? You can push it down a little bit and then it'll generate, and then let go and it'll generate a little bit of force back in the opposite direction. Or you can push it, you can really work and push it down a lot, and then you let go and it does a big force back in the opposite direction. So the direction of the force from the spring is opposite the direction that the spring is being pushed, opposite the displacement of the spring. That's what this just means. It just means how the spring is being pushed. So the more you push a spring, the stronger the force, and the opposite direction is going to be when you let it go. All right, so spring force and tension force in terms of contact forces are pretty straightforward. Air resistance or drag is that force of the air or other fluids as you move through them. They resist that motion. So does anybody have any questions about these last three contact forces?
No, sir.
All righty. So those are our main contact forces, which again are forces that come into play from contact between different types of materials. So even with the air resistance, that object, whatever it is coming into contact with the air as it moves through it. So our field forces, I'm not going to talk a whole lot about them, mostly because they're a little bit more complicated. But again, the main ones to know are the gravitational force, which is just the force of gravity between one object on another, and electromagnetic force, which is essentially just has to do with the force between magnets or other types of electrical charges. So again, gravity is just the force that pulls objects together due to their size. So the Earth is extremely huge, so it has a very strong gravitational force. Everything on Earth is pulled down towards the center of the Earth because of gravity. And then again with magnets, if you get two magnets and you bring them close together, you can feel the force of that electromagnetic field either trying to pull them together, or if you flip it around, trying to push them apart. And again, these are field forces, which means that things don't have to be directly coming into contact with each other in order for these forces to happen. Gravity happens everywhere, all around us, and electromagnetic forces happen whenever these different magnets or different electric charges come into close proximity with each other, but don't necessarily have to be touching in order for the force to be active. All right. So if you remember in that first week of class, last week on a Thursday, we talked about Newton's laws. There is the first law about objects staying in motion or staying at rest until a force acts on them. And that third law about a force from one object to another is an action that creates an equal reaction, an equal force in the opposite direction. And then the second law was a big one that dealt with the main way to calculate force, that F equals ma, force equals mass times acceleration. So Newton, one of the other very smart things that he did before he even really got into his laws of motion, he's the one that kind of came up with this idea of what is a force and how to describe it. And when coming up with these laws of motion, he found that force is proportional to acceleration, meaning that if you put more force in, you'll move something faster, you'll get more acceleration. And it's also proportional to mass. So the more mass that something has, the more force that you need to move it. Again, F equals ma, force equals mass times acceleration. If your mass goes up, or your acceleration goes up, you're going to need more force. And that's kind of what Newton quantified in that second law of motion. So the stronger the force on an object, the greater the acceleration would be. And the greater the mass of an object, the more force you're going to need in order to change the motion of that object. Force equals mass times acceleration. So all of those contact forces can all be calculated based on the mass of the object and its acceleration. So the way that we define, how do you exactly measure force? What is a force? Well, because Newton was the man who described it first, the people who came up with a measurement for it decided to call the unit of force a Newton. And a Newton has kind of a complicated notation. 1 Newton is equal to 1 kilogram meter per second squared, which to you guys, I would totally understand makes absolutely no sense. So a much easier way to think about this is that if you have a 1 kilogram object, so something, here we go. Something about the weight of this textbook, let's say. This physics textbook probably weighs about 1 kilogram, if I had to guess. So if I put in enough force on this textbook to accelerate it at a rate of 1 meter per second squared, so every second this book was going 1 meter per second faster, I would be putting in exactly 1 Newton of force in order to do that. So whenever sometimes you might see things described or forces described in newtons, this is kind of where that basic idea for this unit came from. 1 Newton is how much force you need to accelerate something that weighs a kilogram, 1 meter per second, or 1 meter per second squared. So if something weighed 50 kilograms, you wanted to accelerate it at 1 meter per second squared, you would need a force of 50 newtons pushing on that object. If you had something that was 1 kilogram, like this book, and you wanted to accelerate it at 50 meters per second squared, then you would need to exert 50 newtons of force on the book in order for it to accelerate that quickly. So this is kind of how scientists came up with defining and measuring what exactly is a force, and how can we measure how much force is there. Because again, you look at the mass of the object and times its acceleration. Force equals ma. So they said, okay, if force equals ma, then if you have something that's 1 kilogram and it accelerates at 1 meter per second squared, then we'll call that 1 unit of force, or 1 Newton. So a lot of times when you're dealing with objects, there is not just one single force acting on them. There might be lots of different forces in lots of different directions. And so the way that scientists figure out kind of what exactly the total force and acceleration and direction an object is going to go is by combining forces together. So the simplest way to kind of explain and think about this is that forces that are in the same direction are added together, and forces that are in the opposite direction are subtracted. And so you add up all the forces that are pushing an object one way, and you subtract all the forces that are pulling a force in the opposite direction. And when you do that, you'll get something called the net force. So the net force is the overall force acting on an object. So there are two different types of kind of net of forces that we can think about: balanced forces and unbalanced forces. So balanced forces happen when we have a net force of 0, meaning that all the forces in one direction are perfectly balanced by all the forces in another direction. So when this happens, an object's motion does not change. So imagine like a tug of war match where you have a bunch of like strong burly dudes on one side and a bunch of strong burly dudes on the other side. If they're both pulling on that rope with the exact same force, then that rope is going to stay still, right? It's not going to move very much to either side because those forces are completely balancing each other out. So we have a net force of 0. Same thing where if you're on a like super straight highway in West Texas and you put on the cruise control on your car and you're staying at exactly 60 miles an hour for a while on the highway, the force of your car and the engine on your car pushing it forward is perfectly balanced by the drag force and the friction force pulling it back. So your car will stay at exactly 60 miles an hour because those forces are perfectly balanced. The motion of your car is not going to change. Now, if you need to step on the gas in order to get around some slow poke in the lane, or if you need to hit on the brakes in order to avoid hitting like a cow or something that's on the road, then you're going to be dealing with unbalanced forces. So this is when our net force does not equal 0. We have a larger force and a smaller force. So in one of our directions, our motion is going to change. Either we're going to speed up or change direction or slow down. So we're going to accelerate in some way. And remember, from Tuesday, acceleration is just increasing or decreasing the speed or velocity of an object. So if you're speeding up or slowing down, that's because there are unbalanced forces working on that object. When you hit the brakes on your car, the force of the air and the friction of the tires and the friction of your brake pads hitting the discs of your tires, or not your tires, but the discs of your wheel, is a lot bigger force than the force of inertia that you had going forward. So you're pretty quickly going to come to a halt because you have a lot bigger force slowing you down than speeding you up. Same thing with if you're staying still, if you're on your bicycle and you're stopping at a stop sign and then you look both ways and then you get back on and start pedaling again and start moving forward, you're moving and you're speeding up because the force of you pedaling and putting in that effort and turning that chain and turning those wheels on your bike is greater than the force of friction and the force of gravity that were keeping you in place while you stopped at the stop sign. So you accelerate from that stop. So again, balanced forces are when you have opposite forces that are totally balanced with each other. Your engine is pushing you with 10 newtons of force to the east, but the friction and the air resistance are pulling you with 10 newtons of force to the west. So the net force is 0. You have a positive 10 from the east, you have a negative 10 in the opposite direction going west. So the overall force is 0. So when our forces are balanced, they cancel each other out, and the object either stays at rest or stays at a constant velocity in motion, right? We're back to that first law of motion. Things with balanced forces on them will stay at rest or in motion until some unbalanced force acts on them. So if you step on that gas pedal, you put some more force into your engine, and now your engine is pushing you at 30 newtons east, while the friction and the air resistance is still pulling you 10 newtons west. Now you have an overall force of 20 newtons that is pushing you in the east direction. So your net force, your net overall force causes a change in motion. It's going to cause you to accelerate. You're going to speed up in the east direction because of your force pushing you in that direction. If you're in a car, it's the force of the engine turning the wheels. If you're on a bike, it's the force of you pedaling and physically turning those wheels. So again, another way that we can talk about balanced forces, sometimes physicists like to call it equilibrium. So when things are totally equal, totally in balance. So the net force acting on the object is 0. We're totally balanced with our force in one direction and our force in the other direction. So this is going to cause us to either sit still, so our velocity is 0, we're not moving at all, or travel with a constant velocity. Our car is moving exactly 60 miles an hour in the easterly direction, and it's staying at exactly 60 miles an hour. All right. So does anybody have any questions on the units of force or balanced or unbalanced forces so far? All righty. So the final thing that I want to show you guys tonight are things called free body diagrams. So a free body diagram is a simple little diagram that looks at all of the forces that are acting on a single object. So a free body diagram will have a representation of the object. Usually it's just as like a little square box because, well, it could be any object like a textbook or a coffee cup or a person or a car. You don't need to know what the object is shaped like in order to draw out the forces that are acting on it. So to make things easy, physicists usually just draw like a little box for the object. You then go through and label all of the different forces on the object and use arrows to show what direction those forces are traveling. So we'll look at a couple of different examples to show you guys how exactly you figure out what are all the forces that we're dealing with on these different objects. So probably the most simple example that you can have, you have a textbook that is at rest on a tabletop. So a book sitting on a table. So when something's not moving and it's just sitting there, there's no friction that we're dealing with because nothing is rubbing. There's no air resistance or anything that we're dealing with because, again, it's not moving. So there's only two forces that are acting on it. There is the force of gravity, which is represented by this F-grav arrow down here. And pretty much every single free body diagram that you see or that you draw, if you're doing something on Earth or on any planet really, there's going to be the force of gravity involved. So the only time that you wouldn't have gravity is if you're somewhere in like deep space, far away from any other big celestial object. Otherwise, you're going to have the force of gravity. Then our other force of when something is just sitting on a surface, we have the normal force. So remember, that's the guy that describes the force of essentially just the table holding the book up in the air off the ground in place. So we have the normal force of the table on the book holding it up, and we have the force of gravity pulling the book down. So again, even though it's a book, we can just represent it as like a little box right here. All right, a different type of free body diagram is if you ever watch like the Olympics, like the Summer Olympics, which were supposed to happen in 2020 and maybe are gonna hopefully happen in 2021. And you watch the gymnasts do their thing, and there's one of the ones that they do is they have the bar that's like held up in the air by these ropes that are connected to the ceiling, and then they swing back and forth and stuff on the bar. So for our free body diagram, we're imagining that this gymnast just jumped up there and is just holding on to the bar. So our little object that we're thinking about is the bar. And then, well, really the bar and the person together. So we have, as always, we've got gravity that is pulling downward on the bar and our gymnast. And we also have this force that is pulling upward, which is our tension force. Remember, we don't have a normal force because these guys are just hanging in the air. They're not standing on top of any surface. But the reason that they don't fall down to the ground is because of the tension between the bar and the ropes that are connected to the ceiling. So you have gravity pulling the bar down and the tension force of the ropes that are pulling the bar up. These guys are balanced, so there's no movement that is happening. All right, another simple example. We have a skydiver that is descending and they've reached a constant velocity in the air. And remember this, when people or any object is falling through the air and they hit that constant velocity, physicists call that the terminal velocity, the fastest that you can get while falling through the air. So we have gravity, as always, is pulling the skydiver down to the earth, but the air resistance force, is pushing back up. And so the skydiver is not accelerating. They're falling at a constant velocity because the force of gravity is being balanced out by the air resistance, the drag that they're experiencing as they fall through the air. All right. So now we are adding on a couple extra elements here. This one, a force is applied to the right to drag a sled across some loosely packed snow, and it's accelerating to the right. So some kid is like pulling on their sled and they're running off to the right and they're speeding up as they're going. So the sled is on Earth. So we have gravity that's pulling it down. The sled is sitting on the ground. It's sitting on a surface. So whenever we're sitting on a surface, we have our normal force again that is pushing back on the sled from the ground. We have the force of the kid pulling the sled. So we have our applied force. So the applied force, the FAP is sometimes what it's referred to, is just the contact force of some person or some object pushing or pulling on another object. So in this case, the kid is pulling the sled to the right. So we have an applied force to the right. And then finally, what we can't forget about is because the sled is sliding across the snow, whenever two objects slide across each other, there's a friction force that is in the opposite direction of our applied force. So the kid is pulling and applying force to the right, but friction is going in the opposite direction of that, and so is pointing to the left. So we have our little box here for meaning the sled. We have gravity pulling it down. We have the ground exerting a normal force back up. We have the kid applying a force to the right and pulling it to the right. And we have friction that is happening due to the sled sliding across the ground. And so the friction is pulling it to the left. Another thing to note here is that it says that we have a rightward acceleration of the sled, meaning that our sled is accelerating towards the right. It's speeding up while it's going to the right. So the way that we can show this on our diagram over here, our free body diagram, is that we have a bigger arrow to the right than we do to the left. So the applied force is bigger than the friction force, which is why we are accelerating to the right. So if friction and the applied force were the exact same, if their arrows were the exact same size, that would mean that the kid is just running at the same speed, a constant velocity. But since it says that we're accelerating to the right, we have to make this applied force bigger. So the arrows don't just show the direction of the force, they can also tell us about the strength of the force, the magnitude of the force, how big that force is. And so the normal force and the gravity force are balanced. They're the same size. So we don't have any acceleration up or down, right? We only have acceleration to the right because our rightward applied force is bigger than our leftward friction force. We're overcoming friction and speeding up going to the right. So that is the essence of a free body diagram. You start off with just a very simple picture like a square representing your object. And then you go through and think about all of the forces that are acting on that object. Is the object on Earth? Then there has to be gravity force pulling it down. Is the object sitting on a surface? Then there has to be a normal force pushing up from that surface. Is the object sliding across something? Then there has to be a friction force that is going against the direction that it's sliding is. Is the object sitting on some ropes or being hung up from a ceiling or something? Then there's going to be a tension force along that rope. Is the object moving very, very fast through air or through water? If so, then there's going to be an air resistance force that is pushing back in the opposite direction of the object, just like we had in our skydiver example here. The air resistance is in the opposite direction of where the skydiver is traveling, which is directly downwards towards the ground. But again, these guys are balanced because the skydiver isn't accelerating downward. He's not moving downward any faster anymore. He's traveling at constant velocity. And so if our velocity is the same, that means that our forces are balanced. In this case, the force of gravity is being balanced by the upward force of the air resistance. All right, does anybody have any questions about free body diagrams, what sorts of forces are involved, or what the arrows represent?
No, sir, but I'm like writing my notes, so if you don't change that real quick.
Okay, no problem.
Yeah, I'm the same way. There's a lot to take in, but I might have to go back on the through the class. But I'm good. I think I got it.
Sure, no problem. And remember, the notes are posted up on the Google Classroom, so you can go back to those anytime. And the video will be posted on the Google Classroom right after this class as well. So you're always free to go and look at that as well.
Thank you.
No worries. All right, so for the homework for this one, since I know that we're at like the day before spring break here for night school, I tried to make it a pretty short and simple type of homework. So the first part of it is just matching the correct force to its correct description. So I have a description of each type of contact force that we went over in this left-hand column right here. And then for each one of these, I want you to tell me, does this best describe the normal force? Does it best describe friction? Does it describe drag or tension or the spring force? So for each one, you just match it with what type of force it represents. And then for the second part, we have some free body diagram situations. So I give you a simple scenario, like a book sitting on a table or a crate being pushed to the left. And your answer choices are these different pictures of free body diagrams. And so for each situation, I want you to pick out from these 5 pictures which free body diagram best represents that situation. So we have those two. We have a spider coming down on its silk. We have a air track glider, which is like a little, not like a boat, but like if you ever seen like a air hockey table where it has like the little air coming out of that, for it's kind of like a little mini train type of thing that's traveling to the right. And we have a skydiver falling through the sky. And so for each one of those situations, I just want you to pick out which free body diagram best illustrates that situation. It's set up in a pretty similar way in the Google Docs version, if you prefer doing that one. Again, just matching. Only in this one, I have all of the free body diagrams pictured at the top here. And then you just have to go through and for each one of these situations, match it with the correct free body diagram. All right, so 10 questions should be pretty simple to do based on the notes that we just went over. But does anybody have any questions about types of forces, balanced forces, free body diagrams, the homework, or anything that we've talked about so far here tonight? Anything that you're still really confused about or want a little bit more explanation on?
No, I don't want to say no, and then I do have questions when I start the homework.
Sure. As always, remember, if you're working on it a little bit later and you do get stuck, please reach out to me. You can shoot me a text, shoot me an email, or whatever, and I'll do my best to check on it and get back to you as soon as possible. Again, since you guys are all here tonight, you all have your Thursday attendance credits down. So if you get stuck on a homework problem or you send me a question, but I don't get back to you until like late tonight or tomorrow, don't worry about it. You can turn in this homework at any time. And again, I never do like late grades or anything like that. So as long as you get it turned in at some point before the end of the term, you'll get full credit on it. And you've already got your attendance for being in class today. So you don't need to worry about completing it tonight for attendance.
Okay, thank you, sir.
Mm-hmm.
Good to know.
I think I made a mistake on doing the homework this morning before.
That's fine. You can always go back
Yeah,
and resubmit a different version. I probably won't look at it until late Friday afternoon, or maybe not even until sometime over spring break even.
Oh, okay. Thanks. I might do that. Thank you.
Yeah, no problem. And that goes with any homeworks. If you ever turn in a homework like early, like before class, and then we go through class and you realize like, oh, wait, I didn't fully understand it. I may have made some mistakes on one of those points. You're always more than welcome to go back and turn in another version that you now that you kind of understand it or you've looked at the notes a little bit more. That is always fine by me.